Hi guys, this is topic 6.2 AP Chemistry Energy Diagrams. The learning objective for this particular topic is to be able to represent a chemical or physical transformation with an energy diagram. So it's going to be, we're looking at exo and endothermic reactions and being able to recognize those in graph form. So an exothermic reaction occurs when the energy is released, it leaves the system and goes into the surroundings. That means that the energy levels before and after are lower. So meaning that the energy of the products is going to be lower compared to the energy of the reactants. If it's an endothermic reaction, energy is going to be absorbed from the system, from the surroundings, by the system from the surrounding. It's going to go into the system. That means that the overall energy will be higher compared to the reactants in these products. So we notice we have our labeling here. So whenever we are given a graph, it's best to label our axes correctly. So x-axis can be direction of reaction. Another term can be reaction, RXN coordinate. That's another term you can use as well. Energy or potential energy, just depends. So you can say energy. So the energy of the reactants from here going up to the energy back to the transition state is the EA. And then the level of the reactants, products minus reactants, that's our delta H. The difference in the energy of the products and energy of the reactants is called the enthalpy of reaction or heat of reaction, and it's represented by delta H. The units are kilojoules per mole of the reaction. So in topic 6.8, we're going to look at that later on in the units. Enthalpy of formation. So we're going to look at this more closely then. So the sign for delta H, if it's a negative reaction, if it's negative delta H, it's an exothermic reaction since the products are lower than the reactants. If my delta H is positive, that means it's an endothermic reaction. On the reaction pathway diagram, like we said, we got to label delta H as well as the activation energy. Activation energy is the energy necessary to start the reaction, to break bonds, etc. So the lower the activation energy, the faster rate of reaction. So looking at these really quick, gentlemen, this is just, again, kind of demonstrating the delta H and energy of activation here for the different types of reactions. Exothermic versus endothermic. So be able to recognize and label those. You may also see something called the, what's it called? The energy of activation for the reverse reaction, and I'll talk about that in a specific example later on. So remember the activation energy is used to break bonds, and the energy released from the reaction comes from forming new ones. If more energy is released, then the reaction is exothermic overall. If more energy is required, then the reaction is endothermic. So there's this graph here. We have our reactants, our free atoms ready to go that are broken up to form new bonds in the products. So it says the term is exergonic, and that's a term we're going to look at later when we talk about Gibbs free energy. And it's considered exergonic if the reaction is spontaneous, which we'll talk about later on. Catalysts are added to reactions to increase the reaction rate. They are not consuming the reaction like we've said multiple times. Some catalysts provide an alternate pathway with lower activation energies, as shown here. So notice that the enthalpy does not change, only the activation energy, the transition state level changes. Consider the reaction 2ClF3 plus 2NH3 makes N2 plus 6HF plus Cl2. There's a delta H provided. The enthalpy is negative 1,196 kilojoules per mole of reaction. Draw a reaction pathway for this and then label the products, reactants, and the delta H. So first, let's note that the delta H is negative. So that indicates that our products should be lower than the reactants. There's no specific numbers other than this one here. So by that negative sign, please note that the products should be lower than the reactants. So label the reactants and products. So let's go reactants, products down here. So this is where my delta H will be. So I'm just going to do this. Use different colors, might as well. Delta H is here, and that's going to be negative 1196 kilojoules per mole of reaction. So let's label the reactant. So let's put 2ClF3 plus 2NH3. Then our products is N2 plus 6HF plus Cl2. And let's just say, for example, they ask you to label the energy of activation. It would be here. But they don't give us numbers, so it's okay. Draw a reaction pathway on the graph that has the following characteristics. It tells us that the react doesn't matter what it is. We just have some things we have to worry about. So I'm going to put colors for the different things I'm indicating. So the reactant's energy is 40 kilojoules per mole. Should be about here. The delta H is negative 15. What does that mean? That means that our products would be going down, meaning that it's going to be negative 15. That means whatever I subtract 40 from will give me negative 15. So that means that my products should be at about 25. It tells us, well, that part comes into play. Then it tells us that our EA is at 50 kilojoules per mole. That doesn't mean we're stopping at 50. It means it's going to be 50 plus my reactants. So it's going to be at 90. So then I'm going to use this color to make my whole reaction. So to continue with my labeling, my EA is here. Now that I have this, I can actually do my delta H. Ooh, that's too much. The product's energy is 25 kilojoules per mole. The EA for the reverse reaction. So let's say they asked that hypothetically. So that means you're going to go from where the products are, since I'm kind of like, I'll do it right about here, from the products all the way back up to where that transition state was originally. That's the reverse, the EA for the reverse reaction. So I would label that, let's do, I don't know how we label that. EA -1 because it's reverse. Sure, why not? So then how do you get that? So you're going to subtract remember, it's going to be your transition state minus your product, so 25. So it should be about 65 kilojoules per mole. Use a dotted line to indicate, use a dotted line to show the curve of the same reaction with a catalyst. So notice my levels are the same, like my energy levels for my reactants and products, but now my transition state is lower than it was originally. All right, gentlemen, so if you have any questions, please let me know. Hit the like and subscribe and all that. Thanks, bye.